This is Tom Sargent, and today I'm going to be talking to you about equilibrium, general equilibrium with complete markets. And my text for this is going to be the Chapter 9 of Recursive Macroeconomic Theory by Lars Lundquist and myself. So we're going to be talking about really fun and important things, and we're going to be following in the footsteps of giants like J.R. Hicks, Kenneth Arrow, Gerard Debreu, and we're going to be using an idea that they all used and exploited very heavily. So the idea I'm going to summarize Hicks's idea as saying dynamics is a special case of statics. And what did he mean by that? So here's Hick's idea. So he's writing in the mid-1930s, and he wants to put the ideas of Leon Walras about general equilibrium to work in a dynamic context. And Walras had a model which simultaneously restricted prices and quantities simultaneously on end commodities. So Hicks's idea was, he's had this insight that he could convert this into a dynamic model just by relabeling some of the commodities as indexed by time. So he could have apples at time 0, apples at time 1, apples at time 2. People could have preferences, and there were technologies for converting one into another. And he just applied the Walrasian machinery to that, and he suddenly had a dynamic model. Lots of details had to be filled in. So then about 10 or 15 years later, Kenneth Arrow, he came up with the idea, well, if Hicks did that, why not say uncertainty is a special case of certainty? So the idea there is he's going to index commodities not maybe only by time, but he's going to also index them by state of the world. There's going to be commodities are going to be, a commodity in one state of the world, it rains, is going to be different from a commodity in another state of the world, it doesn't rain. He's going to index that, commodities by that, and then he's going to just do general equilibrium with it. So that's an idea that Arrow and Debreu and McKenzie and Hurwitz and other giants ran with. Well, we're gonna specialize their model, following in the steps of other giants, William Brock of Wisconsin, Lucas, and Prescott. And we're going to specialize it in ways that are widely used in finance, macro, public finance, labor economics. So let's get going. Okay, we're that introduction, we're going to have time. It's going to be indexed by T, and it's going to belong to a set, capital T. And so we're going to have time is going to be discrete and infinite, infinite horizon. Okay. So then at each date T, we're going to imagine that there's some state, ST, we're going to little st, it's going to be a state variable that's going to belong to some set. And typically we'll make this a finite set. Sometimes we'll call it the state space. Then we're going to use this notation. So you can think of game theorists use this a lot. S superscript t is going to be the history. It's going to be the history of. It's going to be the history of st from t equals 0, from, like we could say, from tau. From, it's going to be the history. It's going to be the history of s sub tau for tau equals 0, 1, up to the current t. That's what S superscript t is. In order to use Arrow's idea, we're going to let st be a random variable. So it's a random variable belonging to this set. You can see we're going to put a measure, a probability measure on that set. So st is a random variable. S superscript t is a sequence of random variables, also called, that's a stochastic process. Just another word for a sequence of random variables. Okay. So we're going to put a joint density over those events. And we're going to use this notation. Pi sub t, that's going to be a probability density at t. We index it by t because there's going to be a different density for every history, because the length of these is different. So that's what we mean by a probability. And so what do we mean by this? Well, just over here, we're going to mean pi t of st is positive, non-negative for all st. And we're going to have, it's a probability, so we're going to sum this. We sum this for all st's, sum it over all st's. It's going to sum to 1. And that's going to be true for all t. So we have this sequence of, that's a sequence of joint densities. And then lots of times we're also going to need to talk about, well, since we can do everything with this sequence of joint densities, you notice that, well, we're going to talk about the conditional density of st conditioned on s tau, where t is greater than tau. So we're going to ask, what's the probability distribution of st, the continuation. So st is a, we'll use this language, continuation of this history. That's what this notation means. So we'll often assume that S is finite, and we'll often assume that S0 is given, meaning it was drawn before we started things. So what that's going to mean is that the initial probability distribution over the initial state is 0, is trivial. It's just a probability 1 on whatever was drawn. That's kind of our setup. We'll often assume this is finite. So here's how the economies kind of go like this. If S were equal to this big S, like here's an example. Let's just take a little illustration to keep in your mind. if S is equal to 0 and 1, and if, let's say, S0 equals 0, then the economy kind of unfolds like this. We could draw a picture with these nodes. It starts at 0, and then this is t equals 0. At t equals 1, it could go here, it could go here. T equals 2, it could go here or here. That's t equal 2, so that could be 4. At t equals 3, you get the picture. Okay, so these things, each one of these nodes here, these are different S3s. Those are different histories. You know, we could have 0, 0, 0, 0. We could have 0, 1, 0, 1, and so on. There would be 8 different histories. Okay, so that's kind of the setup that we have in mind. Okay, so so we're going to make things as simple as we can, and still have make contact with the ideas of Hicks and Arrow. And even if we make them simple, there's going to be some subtlety. So here's what I'm going to do. We're going to, in this, right now, we're going to, in this lecture, in this chapter, we're going to stick to a pure exchange economy. We're going to have a pure exchange economy. So there's going to be no production. In a subsequent lecture, we'll alter that. But there's just going to be no, okay. So, but there's going to be people. And they're going to have names. Let's get personal. There's going to be I people. We could call them either people or households or consumers. Same name, households. People call them households, consumers, agents. Those are just all aliases for the same thing. So those all mean the same thing, and they're going to have names. They're going to be named 1, 2, up through I. There's going to be I of them. So there's going to be this set of consumer. I don't know, what do I call it? I'll call this set of people. Set of people. Okay. And what do they do? Well, the way we're going to do this is they have endowments. So in this economy, there's going to be goods. There's going to be actually a large number of goods. It's going to be a large number. What do I mean by that? Well, we have to remember I started with Hicks and Arrow. So with those guys, they played tricks on the number of goods. So there's going to be, at each T, you know, we're making this up in a way that lots of macro and finance people do. At each T and each ST, now there's a lot, because there's an infinite number of those, and depending on how big S is, there's even more of those. So at each T, there is one non-storable. You can't store it. You can trade it consumption good. Okay, that's the deal. At each node, there's one. Okay, and and we're going to, it's owned, it is owned by individual I equals 1 through I. And how is it initially distributed? I'm going to write YTI of ST, it's a mouthful, equals the endowment of the consumption good at, I'll write this, time t and history st. The endowment of person I. So that's what this I index. So the I denotes the person, the T the time, the ST the history. So at each one of these nodes here, for each person, there's some exogenous goods that just drop down from heaven and that person receives. That's the way this goes. And these are exogenous. I'm going to take these exogenous. You may ask, what does exogenous mean? It means outside the model. I'm making them up. And you may ask me why. I'm not giving you a theory of how those things are determined. And good question. It's because I want to study some things. And, later we can create models in which the model also determines the endowments aren't exogenous. They're somehow, maybe you work to get them. But we're just not going to talk about that now, because we want to focus on some other things. Okay, so these are the endowments. So to make this model go, I have to tell you the endowment pattern. Okay, so since I'm a macroeconomist, you're not going to be surprised that I'm going to do this. I'm going to take Y sub, I'm going to add these up from 1 to I, and this, I'm going to do some GNP accounting. It's going to be pretty easy. This is the aggregate endowment. I could call it YT of ST. So that's the aggregate endowment at time t and history st. Okay? Okay, so this is my distribution. This is a distribution across people, and that's my total. Okay. And now I'm going to have to tell you more. Now, I've told you, that this belongs to this, and I've told you that that ST, I've told you what this is, as subscript T. I've told you that. And I've told you that I've said that there's a sequence of probability distributions, joint probability. I've told you this. And now, okay, when people teach statistics, they ask, what does probability mean? Okay. And there's two classic answers to that that, you learn in statistics and econometrics classes. One is they're different answers. One is relative frequency. You can anticipate if you repeatedly draw, I'm going to put this in quotes, independent samples. So you draw independent samples and you calculate, you just calculate fractions. That's what some people mean. That's the frequentist story. So the other thing is, doesn't mean that necessarily at all. This is the story that it's a statement of my, that's an agent, personal, what's my name? My name is I in this setting. My personal beliefs about the likely, I'm going to just be likely outcomes. So this is frequentist, and this is Bayesian. Okay, so so we're going to take, and they're both valid in certain circumstances. If you're kind of liberal and tolerant of other people's beliefs, but soon we're going to have to take a stand on this. Okay, now you'll see why I talk about this. I have to talk about preferences because I've told you about there's people in this economy. I'm going to tell you about their preferences. The preferences are this. Person I, well, first I have to tell you what, I'm going to have to tell you what a consumption profile is. So person I's consumption profile is going to be a mouthful. It's going to be this. CTI of ST for T goes from 0 through infinity. So this is a consumption plan. You could call this a consumption plan of person I. And there's a very large number of those because there's one for each. He or she has to think about consumption at date T at history ST. So at each date, there's potentially a large number of histories. And they're going to go from T equals 0 to infinity. So it's a huge, the commodity space is really big, even though there's one good each period, each history. There's so many histories and so many periods that it's a very big commodity space. So that's what I mean by a consumption plan. So this consumer I is going to have a utility function over those plans. And in micro class, you used to study preferences and different kinds of utility functions, different kinds of preferences. I'm going to represent preferences over consumption plans, and I'm going to do it in a way following Brock, Prescott, Lucas, bunch of finance people. I'm going to really restrict preferences. This is going to be really special. So I'm going to specialize much more than Arrow and DeBrew and McKenzie did. Why? Because I'm interested in some applications. Okay, so here goes. Here's my statement of preferences. First I'm going to make them separable over time. And I'm going to make them separable. See, I'm summing some stuff, separable across histories. And then I'm going to put, I'll do this for a minute. I'm going to give you a discount factor. And then I'm going to put, so we're kind of getting personal. I'm going to put a UI there. I'm going to give you your own function. You could put an I here. That's your own little utility function. One period utility. Now I'm going to put what you get utility from in here. That's just what we did. And now, but these are going to be functions. This is random. So I have to tell you a probability distribution. And I'm going to put an I in here. Okay. Okay. So, so I've written this, and later on in this chapter, we'll actually do this. So notice you can, even though I've specialized stuff very much relative to Arrow and DeBrew, I've quote unquote generalized it relative to Lucas Prescott, because what Lucas and Prescott and Brock would do is they would say, no, this is too much. They're going to erase this. They're going to erase this, and they're going to erase this. So they're going to have a common discount factor, a common little one period utility function, and a common joint probability distribution. Okay, so they erase the I's. Now what you're going to see is when we do the theory, big parts of the theory, but not all, will go through if we don't erase those I's. And as even though I'm erasing the I's, I think it's always a good exercise to back up and put them back in there and see how things change. But the fact that I have erased the I's is going to have content, and it's going to make it's going to have content, and it's going to deliver some of the restrictions of that that are famous parts of the theory. So you know, what I've just shown you is kind of an exam or homework or sometimes even a paper generating function, because by adding the I's in, I can actually get some interesting problems, both in theory and in applications. So having a single, there's one thing, since we're having a single across all I's, this is for all I, this is a piece, this is a part of rational expectations. So in some ways, rational expectations is it's a widely used word, but in some way it's too bad it has misled too many people. So what I'll just say something. What rational expectations would do is it would say the key word is common. And another way to write common is communism. Communism. Why do I write that? Partly to have fun. But this probability distribution is shared by all agents I in the model. And then what I've already told you that. What a rational expectation says, oh, by the way, it's also shared by nature. And depending on your theology, it's nature or God. Or, if you're a econometrician, the data generating mechanism. Same probability distribution. It's shared. And then finally, Lars Hansen, GMM, maximum likelihood, it's shared by the econometrician. That's us. So you could imagine it could be shared by all the agents in the model, but they got it wrong. It wasn't shared by nature. Or it's shared by all the agents in the model and it's shared by nature, but it's not shared by us, the econometricians, because we don't have the right model, and so on. So we could play this. But what rational expectations does is it equates all of those. It's extreme kind of communism. And why is that a good idea? Why was that a good idea? Because a lot of people have thought that's a really good idea. And the reason is, I'll give you a show. Why is that a good idea? Why? I'll say this agnostically. Why have some people thought this communism? I'm not talking about, the former Soviet Union. I'm talking about this. Why this kind of communism is a good idea. And the reason is, some famous people have said, beware of theorists bearing free parameters. So Arthur Goldberger said that. Many people have repeated it. And what this does is it ruthlessly cuts down on the number of parameters. Because if we have a model in which every person in the model has his own probability distribution, we've got to keep track of a huge number of parameters. So this is the reason. So this is it. It makes so rational expectations makes free parameters describing beliefs disappear from our model. That's why many people thought it was a good idea. As simple as that. It's part of a modeling strategy. Okay, and now we're going to put we'll put a restriction on this u. For we're going to require that that u prime is positive, that ui that is differentiable, that u prime is negative, and we're going to require, this is going to be key. We're going to require that the limit as c goes to 0 from above of ui prime of c is plus infinity. This is an Anata condition. And so we want people to hate, they hate zero consumption. That's going to be really important. And I might even forget to tell you that it's really important, because if we alter one of these Anata conditions, if we drop this and allow negative consumption in our model, it's going to carry big implications, especially when we visit some of Arrow's work. Okay. So now I'll describe, kind of the problem of the economic problem. We have a bunch of people. They all have these utility functions that look like this. They like consumption goods. I guess I can do this. I can erase this. I'm going to leave this for now. I've erased every I except I'm leaving this in for now. We're going to erase that later. That's the utility function. Now the job of the economy is to allocate. We want to allocate. So we're going to describe an allocation. It's going to have to satisfy this. A bunch of restrictions. This is at each point in time and each history. This is the total. This is what I call this YT of ST. That's the total allocation. This is the feasibility constraint at time t st. So there's a bunch of feasibility constraints. We're taking this as exogenous. We're taking this as exogenous. But somehow what society is going to have to do is to figure out how to allocate consumption across these across the people. And how should that be done? And we're going to describe two classic methods. One is, you could say it's a command economy. Or planning. Or communism. That's one method. And the other method is competitive equilibrium. And this is going to be decentralization. And that's what we're going to talk about next.